guys, today I want to take a look at a few properties that you will need from time to time, mainly when you're working with proofs in geometry, especially as we work in a more of a formal proof. So I've kind of sneaked a couple of these in already along the way, but I want to take a few minutes and just look at them a little closer, and whenever you need to refresh yourself with properties, you just can click into this track and do that. So let's take a look. I've got 4 of them, and I've talked to you guys a lot about the 4 operations of arithmetic, and we've done that so much if you went through the algebra track, but here they are again. So I've got addition, subtraction, multiplication, and division, and each one of them says addition, property of equality, subtraction, property of equality, multiplication, property of equality, and division, property of equality. You use these all the time when you solve equations. You might not word it this way, and that's fine, because this is a little more formal, but you already know this principle and you already know these properties. So let's see what I mean by that. We were given up here that quantity A is equal to B. Just whatever A and B happen to be, A is equal to B. So what the addition property of equality allows us to do is it says, hey, anytime you want to add the same thing to both sides of an equation, you may do that. You are allowed to do that. Or anytime you want to add things that are equal to each side of an equation, you're allowed to do that. And certainly you know that you do that all the time in algebra. You add the same thing to both sides, and that is what this property really states. It says that if you have A plus B and you want to add, let's say we want to add 3 to both sides, then you could. You could say A plus 3 is equal to B plus 3. It's just that when you are writing a proof, especially a formal proof, a 2-column proof, you always have to put a reason for every step that you take, every step that you write down in your thinking process. So even though this may be second nature to you to know that you can certainly add 3 to both sides, you might not know the property that needs the formal property to put in your list of reasons. So your property is addition, property of equality. Suppose I add to both sides, suppose I add C. A plus C is equal to B plus C. Again, I'm adding the same thing to both sides, addition, property of equality. Maybe I'm also given this. Maybe let's say in addition to being given that A is equal to B, maybe I'm also given C is equal to D. So maybe in a proof sometime I might need to say A plus C is equal to B plus D. When B, C, and D are really the same thing, so if I add C to one side and D to one side, once again, it's the addition property of equality. I'm just adding equal things to both sides of an equation. It's the very same thought process with subtraction, multiplication, and division, so I'm going to go through those very quickly. So addition is done. Subtraction would be if you subtracted both sides, given A equals B, if you subtracted anything that is the same thing from both sides. Say we subtract 4 from A, and then A is equal to B, and then we subtract 4 from B. What is our reason? Subtraction, property of equality. And again, if C is equal to D, then I could subtract C from one side, and I could subtract D from one side, and my reason in my proof is subtraction, property of equality. The same thing with multiplication. If A is equal to B, then I could multiply by 4, or really by anything, and then 4 times A would be equal to 4 times B, and my reason would be multiplication, property of equality. I could multiply by negative. I could go negative 2A is equal to negative 2B, because A is equal to B, and then that again would be multiplication, property of equality, and so forth. I could multiply both by C and go A times C is equal to B times D, and my formal reason is multiplication of property of equality. So you see that it's really the same thing, and the same thing with division as well. Anytime I start with 2 things that are equal and I divide them both by the same thing or by equal things, then again my reason would be the division property of equality. So that's enough of that. You'll hear me repeat that as we go, but I did want to establish those as properties. The next 3 are really used I think they're introduced in some algebra books and some not, but they're used really more and stated in formal proofs in geometry than algebra, although you may already certainly know them from your algebra. But let's take a look. Reflexive property, and this one just says everything is equal to itself. So you're going like, why would we need that? But there are times when you do in a formal proof need to say that A is equal to A or 3 is equal to 3. So anytime you might have something in a proof where you have anything equal to itself, then your reason is reflexive. You might have, in geometry, you would be more likely to have, say, angle B is congruent to angle B. Whoops, I'm running into that. But anything equal or congruent, the reflexive property is true for equals and it's true for congruence. You can use it for either one. But anytime I need to just say, for matters of formality, that something is equal to itself, the reason is reflexive. It's kind of like looking in a mirror and seeing your reflection. You know, that's how I remembered it when I first learned it. Reflection, that's me looking back at me being equal to me. So the next one is symmetric. We don't use this one, I don't use this one nearly as much, but when we need it, we need it. So it says simply that if you have angle A, I'll say, congruent to angle B, that you also have, I don't laugh, angle B is congruent to angle A. I mean, I just switched them. I have two different quantities, and I can say A equals B, or I can say B equals A, and it's the same thing. So occasionally we might use that property, but not a lot. Okay, the next one is the transitive property, and this one is so logical also, and this is what it says. It says if, and I'm just going to use little a, b, and c, but I could be using segments, or I could be using angles, or their measures, but let's just say if A is equal to B, and B is equal to C, then A is equal to C. And again, you see that it's so logical, you might wonder why we need a property, but when you're working with a formal proof, a formal matter, you do need a property statement or a definition, a postulate, or a theorem for every step that you put. So we just need to establish this. Let's go over it again. If A equals B and B equals C, then obviously A is equal to C. We don't have to prove properties. We're given those to work with. So, but we'll be calling it transitive a lot. If it reminds you of substitution, yes, it does. I'm going to leave the differences of those with your teachers because many teachers allow you to use transitive or substitution interchangeably, and I'm just going to leave that with your particular teacher and your particular textbook. If I were saying something like this, if I had, say in one step, I had A is equal to B. Let's say that that was given. And then I had that A was equal to 3. And let's say that that was also given. I mean, then what do I know for absolutely sure? If A equals B and A equals 3, then of course B is equal to 3. And if you put substitution for that step, that's perfectly fine, especially if it's in equals. I use it interchangeably. So I would say substitution or transitive. I'm going to say transitive the most so that you can get used to that. So I would say transitive, and really it could be either one, but it's the transitive property. And so I just want you to take some time to get really comfortable with these properties, or at least to kind of like bookmark them in your mind so you know you can go back to this track anytime you want to and take a look at them so that when you need to use them, they're just tools for you. That's really all that they are. So let's just close this segment quickly and move on into congruent triangles.